before we look at some examples, I want to make an important remark. Cauchy's theorem also holds when G is not abelian. So you remove the word abelian in the theorem. So G is a finite group and P is a prime number that divides order of G, then G contains an element of order P. This is also true. Okay, this requires more machinery to prove, and we do this later in the course. So after I develop more machinery required to prove this, we will prove this. In fact, we will prove what are called Sylow theorems, which contain this and which in fact say much more. So let me give you quickly an example to illustrate the fact that P needs to be a prime number in the theorem. Consider the group so I am going to consider a few 2 by 2 matrices. So 1 0 0 1, minus 1 0 0 minus 1, 1 0 0 minus 1, minus 1 0 0 1. So G is a group of order 4. Okay, so G is a subgroup of, so here the operation is multiplication. So G is a subgroup of GL2R. So I want, and remember these are all, note that these are all invertible matrices. They have all determinant 1 or minus 1. So they are invertible matrices, so it's a subgroup of GL2. And the fact that it's a subgroup is clear. I will give these names. So just for ease of working with this, let's call this E, let's call this A1, let's call this A2, let's call this A3. So G is identity element, I am calling E, right. What is A1 squared? A1 squared is E, that is this matrix multiplied with itself. That is same as A2 squared, that is same as A3 squared. What is A1, A2? Okay, that is if you multiply these two matrices, you will see that it's easy to see that it's A3. A1, A3 is A2, A2, A3 is A1. So this is the entire group structure on this. The data multiplication table is completely given by this. So G is an order group 4 group. So G is an abelian group, of course. And in fact, we have seen in a previous video that any group of order 5 or less is abelian. So this is certainly abelian, and you can see that from I should have written this, that is same as A3 A1. Okay, so that's easily verifiable from the given format. So these matrices are given, you multiply the matrices. If you do not know the matrix theory to see that how to multiply matrices and so on, don't worry about it. Just think of G as a group like this with these operations, with this multiplication table. A1, A2, A3 all have, G has one element of order 1, and 3 elements of order 2. Okay, so as I said, if you do not feel comfortable with the matrix representation, just don't worry about it. Think of G as a group consisting of 4 elements, E, A1, A2, A3 with this multiplication table. They are A1, A2, A3 have order 2, meaning their squares are all identity, and multiplying any two of them will give you the third in any order. So A1, A2 is same as A2, A1, which is A3. This is a valid group and it's a group of order 4. G is called Klein 4 group. Okay, it's called the Klein 4 group. Is it cyclic? Is it cyclic? Is it a power of, is it the group generated by some specific element? It's not, right, because it's certainly not the group generated by E. Is it the group generated by A1? No, because A1 squared is identity. So the group generated by A1 is just EA1. Similarly, the group generated by A2 is EA2, because A2 also has order 2, and same with A3. So it's not cyclic because it has no element of order 4, right? In order for a group of order 4 to be cyclic, it must contain an element of order 4. In this case, it does not. So this is another group of order 4. We have seen that there is a group of order 4, namely the cyclic group of order 4. This is non-cyclic group of order 4, and it's actually an exercise which maybe I'll do later, that up to isomorphism, these are the only two groups of order 4. Both are abelian, one cyclic, the other not cyclic. Now this is an important example to give you various, to illustrate various points. First of all, the converse of Lagrange's theorem fails here. Right, the converse of Lagrange's theorem. What is Lagrange's theorem? If an element in a group, the order of an element divides the order of the group. On the other hand, here 4 divides order of G, which is of course 4, but G has no element of order 4. Similarly, this example shows that P in Cauchy's theorem must be prime, right, because 4 divides order of group. G is a finite abelian group. 4 divides order of G, but G has no element of order 4. The problem is G4 is not prime. So only if a prime number divides order of the group, we can say there is an element of order, that order, and that of course checks out here, because order of the group here is 4, the only prime that divides that is 2, and certainly G has elements of order 2. On the other hand, if G is a cyclic group, of order 4, say G is 1a, a squared, a cubed, then also G has an element of order 4 or element of order 2 in, namely, so Cauchy's theorem applies to this and says that if 2 divides 4, 2 is a prime number, it must have an element of order 2. So it does, because it's a squared. So in this case there is only one element of order 2, because order of a as well as order of a squared, order of a cubed is 2, is 4 rather, order of a squared is 2, order of e, let's call this element e, order of e is 1. So the cyclic group of order 4 has one element of order 1, one element of order 2, two elements of order 4, whereas the Klein 4 group has one element of order 1, three elements of order 2. There is always an element of order 2 in a group of order 4 by Cauchy's theorem, in an abelian group of order 4. But of course every group of order 4 is abelian, so there is no need to separately say abelian. But Cauchy's theorem now says that if you have an order 10 abelian group, it must have an order 2 element and an order 5 element. So here I am doing problems problem 1. So let's start with a couple of very easy problems just to get started. So let's say G is a cyclic group. And let H be a subgroup of G. Then G mod H is cyclic. Okay. So first of all, recall that G is cyclic implies G is abelian. Any cyclic group is certainly abelian, implies H is normal in G. So G mod H is a group. So in order to even say G mod H is a cyclic group, we first need to know it's a group, but it is a group. So we need to now observe that it is a cyclic group. What is a cyclic group? Suppose G is generated by A. So G is equal to A power n, n belongs to Z. So powers of A exhaust all of G. So G is every element of G is a power of A. Now what is G mod H? G mod H is G times H, where G is in G. Okay, so these are the left cosets of H in G. So we claim that, what is your guess? We are trying to show that G mod H is a cyclic group. If G is a cyclic group, G mod H is a cyclic group. In other words, we have to exhibit a generator for G mod H. It's obvious to guess what? If G is generated by A, AH generates G mod H. And this is easy because you take GH for G in G. If G is in G, write G equals A power n for some n, right? Because A generates the group G, every element of capital G is a power of A. So GH is equal to A power nh. But by the operations of cosets, this is just A power AH power n. So G mod H is equal to AH power n, n belongs to Z. Of course, we are not saying that they are all distinct elements. Some of them will collapse. If it's a finite group, for example, they will collapse. But that's irrelevant here. G mod H is generated by AH. So this is the solution. So if G is cyclic, then G mod H is cyclic. And in fact, the coset of the element generator generates the quotient group. Let's do one more problem which is very similar and also very easy. If G is abelian, H a subgroup of G, show that G mod H is abelian. Okay, so as I said, this is also extremely easy. To show a group is abelian, you have to start with arbitrarily two elements of the group. In this case, the group we are interested in showing is abelian is G mod H. So let's take two arbitrary elements, GH and BH. These are two left cosets. What is AH times BH? By definition of the group operation on the quotient group, this is ABH. But AB is equal to BA because your group is abelian, and this is same as AH. Okay, so this is okay. So this is also a trivial exercise. Let's do one more interesting exercise. This is slightly more work, so more interesting. Suppose G, so let ZG be the center of, okay, if G mod the center is cyclic, show that G is abelian. So in order to first solve the problem, let's first recall what is the center. Remember, Zg is all elements A in G which commute with everything else in G. So A in G such that A G equals GA for all G in G, right? So this is the center. So now we are assuming that G mod Zg is cyclic and we want to show G is abelian. Okay, so in order to show abelianness, as in the previous problem, we have to take two arbitrary elements, and to show, we want to show that AB equals BA, right? So let's keep this in mind. We want to show AB equal to BA. So now, since G mod Zg is cyclic, it has a generator, right? It is generated by some element of G mod Zz, right? So this G mod Zz is a cyclic group. It is generated by an element of that, say G times Zg. So an element of this is simply a left coset, right? So take a left coset and suppose that it is the generator. That means everything in G mod Zg is a power of this. So in particular, we have A times Zg. See, A times Zg and B times Zg are elements of G mod Zg. So they are generated by G. So it is some G I and B Zg is some G Zg power J for some integers I and J. Okay, that means because G generates it, these two elements are powers of it. So that means A Zg is G power I Zg and B Zg is G power J Zg, right? This is the meaning of coset multiplication. But now let's pull this relation back to the group G. So this means, so what does this mean? That means A times something, let's say x in the center is equal to G power I times something, where x and x prime are in the center, right? Because A times that, as cosets are equal, that means A times an element of this is equal to an element of this. So A times x will be equal to this. So I can rewrite this as A equals Gi power x for some Zg. Okay, so I mean this x and x prime I am interchanging. So it's actually this x here is x in this x prime times x inverse, because x and x prime are in the center. X prime times x inverse is also the center. So I'm renaming everything to call it x. Similarly, we have B equals G power J times y for some y in the center. So for find, right? So A equals G power I times x for some x in the center. Similarly, B is equal to G power J times y for some y in the center. Now let's go ahead and calculate AB. Now that we have written everything in terms of elements of capital G and not as cosets, let's write AB. So this is G power I x, G power J, y. But now what is x and y? X and y are in the center, so they commute with everything. So this is same as g power I, g power j x y, right? This is g power I plus j x y. On the other hand, what is BA? This is g power j y, g power I x. Again, using the fact that x and y are in the center, so AB equals BU. So I am using the fact that g power I times g power j is g power I plus j, and x and y are in the center. So this shows that because A and B were arbitrary elements of the group and they commute, G is abelian. Okay, so if G mod the center is abelian, sorry, if the G mod the center is cyclic, G is abelian. So the next problem, and this is a problem that I used in the proof of Cauchy's theorem. It says the following: let G be a cyclic group. Suppose that which is finite. So it's a finite cyclic group. Suppose that M divides, M is a positive integer. Suppose that M is a positive integer that divides order of G. Okay, so then show that G contains an element of order M. So that is the problem. So solution. So this is problem 4, I think. Okay. Solution is the following. So suppose G is generated by, suppose that G is generated by A, right? So G is a finite cyclic group, right? So G must be of the form E A squared A power n minus 1, where n is the order of A as well as the order of the group, right? So G is like this. G has n elements and order of A is n. And if M divides n, consider the element A power n by m. Okay, so consider this element A power n by m. See that because m divides n and m is a positive integer, remember m is a positive integer, n by m is also an integer. So A power n by m is a valid element of the group. It's A multiplied with itself n by m times. So A power n by m power m is of course A power n, which is identity. Remember, as I have repeatedly said in the past, you can apply the usual exponential rules to group operations. So A power n by m, so if you call this element B, B power m is E. So B power m is E. Can we say order of B is m? If so, we are done, right? Because we are trying to show that G contains an element of order m. If B order of B is m, we are done. But actually we cannot right away say this. In order to say order of B is m, we have to say more. Not yet. So we can't say this yet. What is order of B? Order of B is the least positive integer D such that B power D is E, right? Certainly m is a candidate for it because b power m is e, but we have to rule out the possibility that something less than m has this property. So if b power d is e, so let's say for suppose for some d less than m we have b power d is e. Suppose that for some d less than m b power d is e, then let's see what are the consequences of this. B power d is e, this means a power n by m. So remember, a power n by m is b, power d is e, right? This means a power n d by m is e. But if d is less than m, n d by m is less than n, correct? Because d by m is less than 1. But this contradicts. We have a power of a less than equal to e, but that power is less than e, n. We have a contradiction. We have contradicted right, because order of a is n means n is the smallest positive integer such that a power n is identity. But here we are getting a power n d by m is e and n d by m is less than e. So this is a contradiction. So this is a contradiction, and only assumption that we could have possibly made incorrectly was that d is less than m. So we must have, so a power m is identity and a power d is identity implies d is at least m. So order of, sorry, b power m, I should not have said a power m, b power m is identity, where b is a power n by m, b power m is identity and no smaller power of b is identity. So order of b is exactly equal to m, and this completes the solution of the problem because we want to show G contains an element of order m, and we have shown that B is that element. And okay, I'll only remark one more time that we have seen the example of Klein 4 group, where you have a group of order 4, yet the group does not contain an element of order 4. Of course, this is also illustrated by the symmetric group on 3 letters S3. S3 has 6 elements, but it is not cyclic, so it has no element of order 6. So the statement that G contains an element of order m if m divides order of G is simply false if G is not cyclic. So let me remark, it is crucial that we assume G cyclic in this problem. Because example, take G to be the Klein 4 group, or G is S3. This has order 4, this has order 6, but no, they are not cyclic. Not cyclic and they have no elements of order 4 or order 6 respectively. Okay, so I'll stop the video here. Hopefully these problems gave you some idea of how to apply various results that we have learned, and you should try to do more exercises that I've been giving in the videos using these ideas. Thank you.